So in this video, we're going to talk about how do we solve a multivariable linear system by hand. So we have, in this case, three equations and we have three unknowns. And by unknowns, I mean we have three variables. And we're trying to figure out, is there an intersection for these variables? So I'm going to go through, or for these equations rather. So I'm going to go through and I'm going to first label each equation. So that first equation I'm just going to call it equation 1, equation 2, equation 3, and so on. If we want to solve something like this by hand, we're going to use a combination of substitution and elimination to help us do that. So let's get started. So if we look at this one, notice I have an x in that first equation and I have a negative x in the second equation. So it would be easy for us to take equation 1 and add equation 2 to it to eliminate the x's. So if we were to add those two equations together, we're going to get this equation, y plus 3z is equal to 5. So we've put two together, we've eliminated a variable, but we need to do the same kind of thing and eliminate x's again using two different equations so that we have another equation that will have y's and z's in it also. So I'm just going to call this guy equation 4 so we don't lose it in the process. So let's put equation 2 and 3 together. What if we were to take 2 times equation 2 plus equation 3. So let's write out what that would look like. If I take 2 times equation 2, I'm going to have negative 2x plus 6y is equal to negative 8. And then equation 3 is 2x minus 5y plus 5z is equal to 17. And now if we add those two equations together, notice the x's are going to cancel. So we have y plus 5z is equal to 9. So that's nice because we have another equation that we have gotten from pairing two of the original equations together that has just y's and z's in it. And now we can put those two equations together with elimination. So what if we were to take equation 4 and we were to subtract equation 5? Let's write out what that's going to look like. So here's our equation 4, y plus 3z is equal to 5. And then we're going to subtract equation 5, which is y plus 5z is equal to 9. Okay, don't forget we're going to have to distribute that negative to everything in here. So the y's are going to cancel. 3z minus 5z is a minus 2z. 5 minus 9 is a negative 4. So that means z has to be equal to 2. So this is really nice because now we know what z has to be. And since we know z, we can substitute back into either equation 4 or 5 and figure out what y is going to be. So I'm just going to go into equation 4. It doesn't matter which one you substitute in, you're going to get the same answer regardless. So if we sub that into 4, equation 4 is y plus 3z is equal to 5. We're going to substitute that 2 in for our z. That means y is going to be equal to negative 1. And now that we know z and y, we can substitute into one of the original three equations and we can figure out what x is going to be. Now, I see that equation 2 only has x's and y's in it. That's going to be the easiest one to substitute in for. Again, it doesn't matter which equation you use, you're going to get the same answer regardless. So let's substitute into 2. So equation 2 is negative x plus 3y is equal to negative 4. I'm going to substitute in a negative 1 for y. So we have negative x minus 3 is equal to negative 4. That means negative x is equal to negative 1 or x is equal to 1. So if we were to look at these equations, our point of intersection is the point x equals 1, y equals negative 1, z is equal to 2. So there's our final answer. So graphically, let's see what's happening using GeoGebra. So if you go to Google and you type in GeoGebra 3D, there is a three-dimensional version, and it will show you what equations look like in terms of three variables. So if we were to graph these equations, that first one is x minus 2y plus 3z is equal to 9. We're going to see this is the equation of a plane, and you can see that green plane here in GeoGebra, and I'm turning it so you can see all the sides of it. So a plane, think about it kind of like a sheet of paper, only it's infinite. It's going to go in all directions. If I graph that second equation, which is negative x plus 3y is equal to negative 4, that's also a plane in 3 dimensions. And you can see now we've got two planes, and there's an intersection for those two planes right along this here, if you can see my cursor there. Now, if we throw that third equation in the mix, now we're talking about a system that has three equations and three unknowns, and we are trying to figure out, is there a single intersection, or are they intersecting in some way, like on a line? And if we were to look at these three, the green, the blue, and the red planes, it does appear that there's an intersection point. And we found algebraically the intersection point is 1, negative 1, 2. And when I plug that in, let me change the color on that so you can see that a little bit better. There it is right there. You can see it. And that is the intersection of all three of the planes. So for this one, there was an intersection on the three planes. And that was at a single point. So let's look at another example. And this one has two equations and three unknowns. So if we were to graph this, we're going to see two planes. So just for fun, let's go back to GeoGebra and let's graph these. So I'm going to delete the last example. We have x minus 2y plus z is equal to 2. So there's our first plane. And then we have 2x minus y minus z is equal to 1. And there's the second plane. So you can see if we rotate that there is an intersection. This is going to be an infinite intersection, which means that we're going to end up basically with the equation of that line in 3 dimensions, only it's going to be written in something called parametric form, which we'll talk about in just a little bit. So once again, I have equation 1 and I have equation 2. So just like before, we want to put these equations together so that something cancels. So here's what I see. And there's lots of different ways you could go about doing this. But I see if I take equation 1 and I add equation 2 to it, then I'll cancel the z values. So let's do that. If we add equation 1 and equation 2, we're going to have 3x minus 3y is equal to 3. Now, we already know there's an infinite number of solutions because we looked at what this picture looks like. And what's going to happen is that we need to be able to solve and write that line in 3 dimensions as x equals something, y equals something, and then we're going to let z be a free variable. And what that means is that z can take on the value of any real number. So if we were to take this equation and we were to solve this for x, we're going to have 3x is equal to 3y plus 3. Divide everything by 3 to get x by itself. We're going to get x equals y plus 1. So now we're going to take this information and we're going to do a substitution. Let's substitute into that first equation. It doesn't matter which one we substitute into. I'm just going to choose to substitute it into the first. So that first equation was x minus 2y plus z is equal to 2. If we substitute in for that x,
that is not correct.
We're going to get that. And then if we combine like terms, we're going to have negative y plus z is equal to 1 just by moving that 1 over. So negative y is equal to negative z plus 1, or y is equal to z minus 1. So we've rewritten y in terms of z, but notice now we have a substitution that we could plug back into this y. And we can rewrite this in terms of z also. The goal is always to write x and y both in terms of the same variable z. So that's why we need to make that substitution. So we're going to substitute. X equals y plus 1, but now we know that y is equal to z minus 1. So that means that x is equal to z. So we have x is equal to z, y is equal to z minus 1. And then z can take on any real number. Now, in this case, I chose to keep z as my free variable. You could go through and you can make x your free variable and then write y and z in terms of x. That's perfectly fine. But most of the time, we usually just use z as the free variable. And that goes into another course in something called Gaussian elimination, which if you take linear algebra, you'll get to talk about. So good times coming up in future courses.